Okay, so now that we've had a little introduction into the calculus of variations and had some example problems, I'm going to be going over this video. One of the things that will require for the two-dimensional isoperimetric problem, which is generalizing um, the Euler-Lagrange equation to work with parametric curves. And so before I do that, I'm going to outline like the outline of the proof of the isoperimetric problem that we'll get to later. So that you know where the next couple of videos are headed. So what we're going to do is, instead of looking at functionals of the form j of y, where we have y as some function of x, we're going to look at like functionals of parametric curves. So what that'll be is like we can have some parametric curve gamma of t, which is just some coordinates x of t t and y of t. So t is just some variable which varies over some interval, let's say 0 to 1. It doesn't really matter what the interval is, as you'll see later. But you can think of this as sort of time, and then as time progresses, you sort of trace out some curve. So this will be your curve gamma, and then at any point in time, you have your x coordinate and your y coordinate, and these are both functions of time. And so we'll have functionals j of gamma, which in general will look like integral from 0 to 1 or whatever your domain range is. And this will look like something like f of t, x, dx, dt, y, dy, dt, and yeah, that's it, dt. And so this is similar to what we had before, where we had the integral from 0 to 1 of f of x, y, dy, dx, integrate with respect to x. But the difference is now we're using t as our independent variable instead of x. Hopefully that doesn't cause any confusion, but now x is like a dependent variable which depends on the time t. So in this video we'll show an Euler-Lagrange equation for this, which will allow us to, or like a set of Euler-Lagrange equations, which will allow us to find extremal values for functional of this kind, which means that, say, like this functional represents what the area of this curve is, or this closed loop, then an extremal would be a curve that either minimizes or maximizes the area. And if it's the arc length, then it's a curve that minimizes or maximizes the arc length. So then what we'll do is we'll derive two different functionals, j1 of gamma and j2 gamma. And so what these will correspond to is one of them will correspond to area and the other one will correspond to arc length. So the problem is the following. Optimize j2 of gamma. Again, gamma is just some parametric curve. If j1 gamma is equal to some fixed area A. So what this is saying is this is some functional where you feed it in the parametric curve that you're working with, and it will spit out the area enclosed by that curve. So that'll be like this area over here. This is some functional which you spit in, or you give it the parametric curve, and it'll spit out the arc length, which is the arc length out here. So this is saying, say you fix the area to be A. So like this has an area of A, maybe this longish rectangle has the same area. But these two guys have different arc lengths, or perimeters, I guess. And so it's saying if you fix the area, what is the optimal value of this for all the curves that have this fixed area? And so then you'll see that you can use something very similar to Lagrange multipliers, which I'll make another video on. And so if you want to solve this sort of problem, that's the same thing as solving the problem of optimizing a functional which looks like the following. So you create a new functional called j of gamma, which is equal to j2 gamma plus lambda j1 gamma. And so this will be like, if this is the integral of f1 dt, and this is the integral of f2 dt, then this will look like the integral from 0 to 1 of f1 plus lambda f2 dt. So then you optimize this, and then to calculate the value of lambda, you look back at this equation. So if you're taking some multivariable calculus, you may realize that this is actually the same procedure that you have for optimizing things in multivariable calculus using Lagrange multipliers. And the way that that works is that if you have two functions f, g, which go from like three-dimensional space to the real numbers, then if you want to optimize f if g is equal to some constant, then what you do is you set gradient of f is equal to lambda times gradient, how do you draw a triangle? Gradient of g. And so this is just saying that their derivatives are proportional to each other. And here you have three variables from here, three variables from here, and you also have this unknown variable lambda. And so the fourth equation you have is j equals c. So this gives you g equals c. So this gives you four variables, three equations, and this is your fourth equation. So this is four variables and four equations, which you then solve for x, y, z, and lambda. And here similarly, you'll find that this is essentially the same thing as saying delta j1, which is our functional of h is equal to lambda times delta j2 of h, which is our functional for our second thing. Well, I guess the lambda would go here because we're calling this one j1. But it doesn't really matter. Anyways, so here you have your sort of analog to the derivatives being proportional. And then you solve for the value of lambda by using this equation that j1 of gamma is equal to the area. So after solving out to this Euler-Lagrange equation, or the Euler-Lagrange equation that you get by solving this out, you'll pretty much get the differential equation for a circle, and then you'll find out that you actually don't need to solve for lambda or any additional constants that you might get, and it's pretty easy to see that it's a circle. So in this video, I'll be talking about this, so functional of this form and creating an Euler-Lagrange equation out of that.